Hi, today we're going to prove the maximum principle for the heat equation. Recall that the heat equation is UT KUXX, which means that UT minus KUXX should be equal to 0. Additionally, we're going to impose some domain restrictions on this. We're going to say that x lies between 0 and L, and that t lies between 0 and capital T, right? This means that we have a domain that looks something like this. Right? The idea of the maximum principle is that the maximum of the solution to the heat equation, right, so our U, is going to occur somewhere along these red lines here, right? Notice that this does not include T, right? So the idea is that the maximum, right, the largest value of U is going to be somewhere on x is between 0 and L and t equals 0, or x is either 0 or L and t equals whatever you'd like, right? As long as it's not capital T. So how do we prove this? The proof relies on a very common technique in partial differential equations and then in a lot of math outside of PDEs. And the idea is that we're going to perturb the solution, right? So what does that mean? Well, we're going to suppose U is a solution, right? That means that U satisfies U sub t minus U sub xx, minus k U sub xx equals 0, right? Now we're going to let V equals U but perturbed slightly, and that perturbation is going to be epsilon x squared, right? This is going to seem a little arbitrary at first, but it'll become clear why we chose this in a second. It basically just works out very nicely, right? Now this epsilon here is going to be small, and we're later going to take the limit of epsilon as it goes to 0, right? Also a very common technique. You'll see this sort of epsilon notation quite often, right? Okay, so now let's plug it into the heat equation, right? First, let's find what the derivatives of this of V are, right? So that we can plug in. Well, the partial derivative with respect to t, we ignore the x, it falls away, we just get ut. Double derivative with respect to x is going to be uxx. By the linearity of the differential operator, we're going to get uxx plus 2 epsilon, right? That should follow pretty clearly. All right, that means that plugging into the heat equation, we get Vt minus kvxx is equal to ut minus kuxx minus 2k epsilon, right? We just distributed that k, right? We just distributed that k here. Well, if we allowed u to be a solution, that means that this is 0, right? That means that this is Vt minus k Vxx is equal to negative 2k epsilon. Now, another detail that I forgot to include is that epsilon is small and epsilon is positive, right? We can allow epsilon to be whatever we want. If we say it's positive, it'll be positive, right? So if epsilon is positive, that means that this whole term is negative, right? Positive times a negative is a negative. That's a pretty elementary algebra, right? Okay. Well, now we start thinking, what if there's a minimum inside the boundary, right? Right? Boundary of the domain, that being. Right? Well, then there's a couple of things that we know from just regular calculus, right? We know that v of t should equal 0, and we know that vxx should be less than or equal to 0, right? That's just sort of the principle of concave down, right? Now, we chose these specific two derivatives to talk about, right? Because they are the derivatives that appear in the heat equation, right? We could have chosen v sub tt, right? But these we can plug in, right? So note that if vxx is less than 0, that means that vxx multiplied by negative k should be greater than 0, right? Greater than or equal to 0. Well, that means that with vt equals 0, this here becomes 0 minus kvxx, which is greater or equal than 0 is equal to negative 2k epsilon is less than 0, right? So I can even get rid of this 0 here. Well, what does this say? This says that kvxx, negative kvxx, which is equal to negative 2k epsilon, is less than 0, but it's also greater than or equal to 0. And note that this less than 0 does not include 0 itself. If it did, well, then it's just 0, right? Because it's bounded up. It's bounded by a high bound of 0 and a lower bound of 0, right? But because this is a strictly less than 0, this means that we have a contradiction. Right? So, I'm sorry, this should be max. So the max must occur on the boundary. Right? Because we have a contradiction if we suppose that it occurs inside the boundary. Right? Okay. Well, this is the max for v. We should know. Max v, right? Now we want to show that this also holds for u, because recall v equals u plus epsilon x squared, right? And once again, now we realize that we chose that x squared so that it becomes 2 epsilon when we take the double x derivative, right? Regardless, we now want to show that this is the case for u as well. Well, this turns out to be fairly easy. We just sort of have to reason through it. We have that vxt must be less than the maximum of v, maximum of v on the boundary, right? We've just shown that, right? Because the maximum on the boundary is going to be the maximum of v in general, right? And this is the definition of a maximum. We also have that since v equals u plus epsilon x squared, that vxt is less than or equal to the maximum on the boundary of u plus epsilon L squared, right? We just plug in the boundary conditions here. We could have plugged in 0, but here we're gonna plug in L squared, right? Well, now, so if v is equal to u plus epsilon x squared, that means that that this expression here is also less than or equal to the maximum on the boundary of u plus epsilon L squared. Right? Well, we're free to just move things around, right? This is just an inequality, which means that we can say that u is less than or equal to if we subtract on both sides epsilon x squared, we get u is less than or equal to the maximum on the boundary of u plus epsilon L squared minus x squared, right? Well, now we can just take epsilon goes to 0, right? We said that we would do that, and I'm not gonna lie to you. So we let epsilon go to 0, which means that this whole expression here goes to 0, which means that u is less than or equal to the maximum on the boundary of u, right? Well, what does that say? It says that no matter what u is inside, right? I'm sorry, no matter what u is at all, it's never going to be more than the maximum value of the boundary on the boundary of u, right? So in other words, u has maximum on the boundary. QED end of proof. A couple of more remarks are in order. First of all, notice that negative u, if you use a solution, negative u is also a solution. To the heat equation, right? That means that we can apply the maximum principle to negative u as well, right? And what you end up getting is that the maximum of negative u is just the minimum of positive u, right? So this gives us the minimum principle. I encourage you to just try it yourself, right? But it's fairly easy. You can just argue that negative u is also a solution, and so its maximum must occur on the boundary, right? The maximum of negative u is just the minimum of u, right? And lastly, sort of, I just want to talk about why the above proof implies that the maximum has to occur in the boundary, right? The reason is that if you think about, let's sort of reduce this to one dimension here. Like, we're just gonna say this is some f of x, and this is x, right? Say we have a function with a local maximum, right? Well, the local maximum is exactly what we were talking about, where f prime of x is equal to 0, right? At this maximum, and f double prime of x is less than or equal to 0 at the local maximum, right? But at sort of, loosely speaking, a global maximum, well, then you can have sort of a function like this that at the very edge attains its maximum, right? At the very edge of the boundary, right? Well, it's not necessarily the case that f of x there is going to be 0, right? Clearly, this function has a non-zero derivative here, right? And also not necessarily the case that this is true. And so it follows that if we impose these two conditions, right, which we sort of did just with a different variable, because we have a multivariable function, it follows that if you impose those conditions, you're working with a local maximum, right? So what we've essentially shown is that you can't have a local maximum. You basically just have a global maximum, where global means it's just sort of at the boundary here, right?